Okay. Hi everyone, welcome back. So last time we talked about stochastic process, right? That is a collection of random variables, and our discussion was mainly focused on the Bernoulli process and Poisson process, right? Okay. Well, how do I? Okay, you got it. Okay, so how do I access? The menu has been a little bit changed. Okay, let me do this. Down. Okay. Let me use the smart board. Okay. Close. Okay, so last time we've considered a single experiment, right, whose outcome can be classified as either a success or failure. Is that right? So we considered x equals 1 if success, right? And 0 otherwise. And this x follows Bernoulli distribution with parameter p, right? What is P? P was the probability of being a success. Outcome becomes success, right? So we considered this single experiment last time. Is that right? And then if you make this single experiment, let's say n times independently, okay, then the Bernoulli random variable counts the random number of successes within those n different trials. Is that correct? And then again, if you make this single trial independently over and over, then the geometric random variable counts total number of trials until you got the first success. Is that right? And then what is the Pascal or negative binomial variable? Let's go back here. The Pascal random variable or negative binomial random variable is a, you can pick up, yeah, is a generalization of the geometric random variable. So it just count total number of trials required for you to get the kth success, okay? So k is not equal to 1. If k equals 1, then it just go back to the geometric random variable, okay? And what is the, okay. And then one thing important, when you consider the Bernoulli process, is that because in the Bernoulli process, each random variable is independent each other, right? And then each random variable follows Bernoulli distribution. That's why when you consider this Bernoulli process, you always think about the probability P, okay? You always utilize the probability P for any way, for some way, okay? So that's very important thing. Keep in mind that. Bernoulli process has two important property. What is that? Each random variable in the Bernoulli process, they are independent each other, and each random variable follows Bernoulli distribution with parameter P, okay? Okay. Then let's move on to the Poisson process. What is the Poisson process? Last time we talked about it as well. There is a special case of counting process. Do you remember that? Okay. So basically, it counts the total number of kind of events, okay, which has been occurred in a certain time interval, okay. And also, it has two important properties. Does anybody remember that?
The average rate, average rate or arrival rate, mean.
No, the property, important property of the Poisson process. Independent increment and stationary increment, okay? So, and the Poisson random variable here, the first one, is a count of the total number of events that occur during a certain given period of time, okay? And the time between arrival follows exponential distribution. Also, the exponential distribution measures the time needed for the first arrival, okay? And the k-Erlang distribution measures the time required, needed for the kth occurrence, okay? So, can you distinguish those random variable from the other side, okay? So, important thing when you consider the Poisson process is that you always use lambda, okay? That is some kind of average rate, okay? Average, the arrival rate, for example, at the intersection. So keep in mind that this diagram, and then today we are going to solve many different example problems, okay? So our first example is this. So two evenly matched baseball teams are playing in the World Series. So that for any one game, each team has 50% of probability of winning. And the series is over as soon as one team wins 4 games. Okay? Then we'd like to know the probability that the series will be over in exactly 4 games. Okay? So how do you handle this question? First of all, let me ask you, so which process, which stochastic process do you have to use? Bernoulli process or Poisson process? Bernoulli? Why is that? By reading through this problem description, you get an important information, which is probability of 50%. Okay? Do you remember? So when you consider Bernoulli process, we're going to use probability. Okay? Not the lambda. So in this case, since the probability value of 50% is given, so highly likely we're going to use Bernoulli process. Is that right? Okay. And then what distribution you're going to go with within the Bernoulli distribution, Bernoulli process? Binomial? How do you know that?
We want 4 successes and 4 tries.
Okay, yeah, that's good. So I would define the random variable first. Okay? Every problem, the very first step for me is to define random variable. So in this case, I would define the random variable. Okay. Let me. Is it good? Okay. Okay. So this one is good. So I define, let me put it up here, n sub 4. That is the number of wins, okay, or number of successes, okay, number of wins in the first 4 games, okay, or in general, n sub 4 can be the number of successes in the first 4 trials, like that, okay. So do you remember Bernoulli, the binomial random variable counts the random number of successes within a specified number of trials, right? So this is it, right? Exactly. So n sub 4, of course, follows binomial distribution. Is that correct? With n equals 4, right? And then what is p? P is going to be 1/2, 50%. Does that make sense? So the next step is using the random variable we just defined, which is n4. We need to come up with the desired probability. What is the desired probability in our case then? That's going to be probability n sub 4 becomes 4, equal to 4, right? Does that make sense? That's going to be 4 combination 4 and then 1/2 to the 4th power 1 minus 1/2 4 minus 4, okay, power. Or simply you can say that the probability that the, let's say the National League team wins 4 straight game would be 0.5 to the 4th power, which is 0.0625, I believe. Likewise, the probability that the American League team wins 4 straight game would be the same, right? So the probability that either the National League or the American League team wins 4 straight game would be 2 times of this. Is that right? So 2 times 0.0625 would be 0.125, I believe. Either is fine. Okay? But I want you to get familiar with what he did earlier here. Okay? So whenever you have certain problem description, try to define the random variable first, and then use that random variable to come up with the desired probability. Okay? That's what you are going to do. Okay? For the rest of today, and probably next hour as well. Okay? Okay, now let's take, do you need more time? Okay, then what about the next question? The maximum number of games required in the series is 7. Then we'd like to know the probability that all 7 games are required. So when does the 7th game is required? When?
They didn't reach 4.
Yeah.
So 7 minus.
So in other words, the 7th game is required if after playing 6 games, the National League team, therefore the same for American League team as well, has won only 3 games each, right? Then the 7th game is required. Is that correct? Right? So for example, let's say this is the first game, second, third, fourth, fifth, sixth, and 7th game. Let's say American League team wins the first 4 games, then of course 5th, 6th, and 7th game will not be required. Is that right? Okay. So in that case, I'm going to define n sub 6. Okay? So that's going to be the number of wins within 6 games. Okay? Then of course the number of wins by the National League team when 6 games have been played will have the binomial distribution with n becomes 6 in this case, and the probability is same as before, 50% of chances. Is that right? So in that case, the desired probability should be n6 is equal to 1. Total number of wins within 6 games would be equal to 1.
3.
Is equal to 3. So 6 combination 3.5 to the power 3. 1 minus 0.5. 6 minus 3. Okay? So you're going to get certain value in the end. Also, in this case, I just let you know, we can get the same answer using different random variable. Which random variable we're going to use? If I define, let's say, t sub 4, that's the time of the 4th win. Okay? Then t sub 4 follows which distribution? Time of the kth success is 1.
Geometric distribution?
No, k is in this case 4. It's not equal to 1. Pascal distribution. Okay? So in that case, t sub 4 follows Pascal distribution. Okay? So in that case, we're going to have t sub 4 equal to what? 7. The number of games that required 4th win should be equal to 7. Does that make sense? Are you following me? So in this case, 7 minus 1, 4 minus 1, 1 minus 1 half, 7 minus 4, 1 half, 4 minus 1. Then you're going to get the same answer, I believe. Okay? So for this problem, we can solve by using the binomial distribution or using the Pascal distribution. It's up to you. Okay? It depends on how you define the random variable. Okay? Okay, so can you move to next question? Okay. Okay, so in this case, we're dealing with a pair of dice. So we want to know the probability of throwing a 7 at least twice in 5 throws of a standard pair of dice. Okay, of course we know that there are 36 different outcomes when you throw a pair of dice. Is that right? 6 by 6 becomes 36. Is that right? So there are 6 times 6, 36 different outcomes you're going to get. And then, how many of them you're going to get a count of 7? How many different cases? You're going to have 1 plus 6, or 2 plus 5, is that right? 3 plus 4, or 4 plus 3, 5 plus 2, 6 plus 1. Okay? So we have 1, 2, 3, 4, 5, 6 different cases that you will come up with the count of 7. Is that correct? So, in that case, I'm going to define n sub what? N sub 5. What is n sub 5? That is the number of throwing a 7 in the 5 trials. Does that make sense? Okay. So I define the random variable n sub 5 is equal to the number of throwing a 7 in the 5 trials. Then of course, the number of 7s rolled in those 5 throws of dice will have binomial distribution. Is that right? Of course, n becomes 5, right? And then p becomes what? 6 out of 36. That's going to be the winning probability, right? Success probability. 6 out of 36, which is 1/6. Right? That is our probability. Because there are 6 different ways to get 7, right? So 6 out of 36 would be the probability P. Does that make sense? So using this random variable we just defined, we need to come up with target probability. How's get it? N sub 5 is what? We want to know the probability of throwing a 7 at least twice. So it's got to be at least twice. So greater than equal to 2. Does that make sense? Okay? So that's going to be probability n sub 5 equals 2. Probability n sub 5 equal to 3. N sub 5 equal to 4. Oh, sorry. It's going to be 4. And then plus probability n sub 5 equal to 5. Okay? Of course, because we don't have enough space, I'm going to just write down the first term, which is 5 combination 2, 1 over 6 to power 2, 1 minus 1 over 6, 5 minus 2, and so on. Okay? Then, from my previous computation, I got 0.19625. Okay? But I want you to make sure you're going to get the same answer. Otherwise, let me know. Okay? Any questions so far? I believe I gave you the solution for the radio keys show problem. So please make sure that you understand this at home. Okay? So let's move on to the next example. So in this example, we assume that the number of cars passing over a toll bridge during the time interval 10 a.m. to 11 a.m. Is 240. And the cars pass individually at random. Okay? Then we'd like to know that the probability that not more than 4 cars will pass during the 1 minute interval from 10:45 to 10:46 in the morning. Okay, so in this case, first of all, we're going to assume that the arrival of the cars forms a Poisson process, okay, with the arrival rate lambda is equal to 240 cars per hour, okay? Of course, that's going to be 4 per minute, is that right? Because there are 60 minutes in an hour, so 240 divided by 60 becomes 4. So it's the same, right? 240 per hour is identical to 4 per minute, is that right? And the given period is t equal to 1 minute, right? Because we want to know that the probability that no more than 4 cars will pass during the 1 minute interval. So we're going to set t equal to 1 minute, okay? So in this case, how are we going to define our random variable? Which is n sub 1. Okay? So what is n sub 1? Total number of cars passed during the 1 minute interval. Okay? So that's going to be total number of cars passed during the 1 minute interval. Okay? Then what is the desired probability? Probability n sub 1 is 1. We want to know the probability that no more than 4 cars will pass during the 1 minute interval. So what is the desired probability? How do you set it up? N sub 1 is less than equal to 4, right? Because not more than 4 is less than equal to 4, okay? Because n sub 1 follows which distribution? Poisson, right? Obviously, we are dealing with lambda. So it's going to be one of the Poisson process, right? And simply Poisson random variable counts total number of arrivals or total number of events within certain time interval. So this follows Poisson distribution with lambda equal to 4 per minute. Because we are supposed to use same unit, right, within one problem. That's why I converted lambda value from 240 per hour to 4 per minute, okay? Because the t value is 1 minute, okay? We are supposed to use the same unit within the one problem. So in this case, that's going to be summation over x equal to 0 to 4, right? And then lambda t to the power x over x factorial e2 minus lambda t. Okay? So we already know lambda is 4 per minute, t is 1. So you should be able to get this value, right? And then in my previous computation, I've come up with 0.6288. Okay? But I want you to make sure that you're going to get the same value. Otherwise, let me know. Okay? Does that make sense to you so far? Okay. So let's move on to the next example. Okay. A sampling inspection plan calls for the inspection of 50 items out of a lot of 1,000 items. If there are no defective items in the sample, the lot is accepted. Otherwise, it is rejected. If a lot of 1% defective items is received, what is the probability that it will be accepted? So, which distribution you're going to use? First of all, I have to define random variable, as always. Okay? So how do you define the random variable? How about n sub 5? What is n sub 5? Total number of defective items found in the sample of size, it should be 50. In the sample of size 50. Okay, so that is the number of defective items found in the sample of size 50. Okay? Then n sub 50 follows which distribution? You remember, binomial random variable counts random number of successes within a certain number of trials. Okay? So this is it. So n sub 50 follows binomial distribution. Okay? So follows binomial. N is 50, of course. And what about P? What is P? 0.01. Is that right? So in this case, finding a defect would be defined as the success, okay, in our case. So in this case, the desired probability would be probability n 50 equal to what? Equal to 0, right? That is the desired probability. Okay? Because if there are no defective items in the sample, the lot is accepted. So, right? So it's going to be equal to 0. So that's going to be simply 0.01 to the power 0, and then 0.99 to the fifth power, which is 0.605. Okay? So to be accepted, make sure number of defective items should be 0. Okay? And in this case, probably we can also go with Poisson distribution. So in that case, because you remember earlier I mentioned that if n times p is less than 5 and n is 50 and is larger than 50, we can go with Poisson. If np is greater than 5, then usually we can go with binomial. And somebody tell me if this is not accurate, if this is not true, then let me make a correction later. But that's what I remember at the moment. Okay, but this is kind of borderline. Okay, because in that case, n is equal to 50. So let's see, what if we use Poisson distribution? Then what value will come up with? Okay, so that we can compare with this probability value later. So if you use the Poisson random variable to use the approximate binomial random variable, then it's going to be n 50 equals 0. Same probability, so 0.01 times 50, and then to the power 0, and then 0 factorial times e2 minus 0.01 times 50. Okay? Then I come up with 0.606, which is very similar to this value. Okay? So in this case, it looks okay. It depends, but for me, it's okay. You can go either way, either binomial distribution or Poisson distribution. You remember, if n is pretty large and p is pretty small, but in this case n equals 50 is not big enough, I believe, and p value, which is 0.01, is pretty small, right? So I think either way looks okay. Okay, so let's move on to the next example. A carnival ride having 6 seats lasts for 5 minutes. Persons wishing to ride arrive according to a Poisson process with arrival rate, which is 2 per minute. And let's suppose a ride cycle has just begun and there are no persons waiting. In that case, what is the probability that the next ride will be filled to capacity? So in that case, we assume that the arrivals of the person, of the people who wish to ride form a Poisson process with arrival rate here, which is lambda, okay? 2 per minute is lambda, okay? And we're going to define random variable n sub 5. What is n sub 5? Number of people arrive in 5 minutes, the next 5 minutes. Number of people arrived 5 minutes. Okay? So in that case, t would be 5 minutes. Okay? Then of course, n sub 5 follows Poisson distribution with lambda equal to 2 per minute. So probability that during the next 5 minutes, what do you want to know? The next ride will be filled to capacity. When does the next ride will be filled to capacity? When? During the next 5 minutes, if 6 or more people wish to ride, right? Then the next ride will be filled to capacity. Is that correct? So the desired probability should be, let's say, probability n sub 5 is greater than equal to 6. Is that right? Which is equal to 1 minus probability n sub 5 is less than equal to 5. Or the same probability n sub 5 is less than 6. Those are identical. Is that right? So using the Poisson distribution, I come up with 0.93 to 9. Okay, I want you to double check this value. Okay, what about next example then? Suppose that there are 4 customers already waiting in the line, the last of which arrived 20 seconds ago. You hope to ride on the next cycle, which begins in 2 minutes. But you must first put your coat in a nearby locker, which will take 1 minute. Then what is the probability that you will be able to ride in the next cycle? So obviously you have only 1 minute left, right? Until the next ride. So you will be able to ride in the next cycle if during the next minute while you are gone, no more than 1 person arrives for the ride. Is that correct? So if I define n sub 1, is that right? N sub 1. That is the number of people, number of person. Who wish to ride within the next 1 minute. Okay? Then the desired probability should be probability n sub 1 is what? Is less than equal to 1. Okay? Are you following me? Does that make sense? So that's going to be sum over x equals 0 to 1, 2 to x, x factorial, e2 minus 2. Okay? So I come up with 0.4060. I can get the same answer using other way in this case. What other distribution you can use in this case? Already, I'm gonna define let's say t sub 2. That is the arrival time of the second person. Then t sub 2 follows which distribution? That is the time of kth arrival, kth event. What is that? L-long distribution. So in that case, it follows 2 L-long distribution. Okay? So using the t sub 2 random variable that I defined just ago, we can have the target probability, which is t sub 2 is greater than 1 minute. Okay? Arrival time of the second person will be occurred after 1 minute. So it's got to be greater than 1. Okay? Does that make sense? Okay, so this is the last example for today. But before we do that, because we have a new face, so why don't you introduce yourself? Because last time we did it, just briefly, no pressure. But
my name is Ayat.
you're a new student, right?
I'm a new student, yes.
Okay.
Yeah, it's my first semester, yeah.
Okay,
and this first lecture also.
Oh, okay. And
Yes.
you're in our master's program, right?
Master program, yes,
Okay.
for industry and engineering, yeah.
Okay.
Yes, nice to meet you all.
Okay. Thank you. Okay. So in this last example, to say in a transmission line, there is a fault in the insulation every 2.5 miles on the average. And we want to know the probability of having 2 faults in less than 6 miles. Okay, so of course we're going to define the random variable first, right? So how do you define random variable? Poisson? So you mean you're going to define something n sub what? 6. That's a good way. So how do you define n sub 6? That is the number of faults occurred within 6 miles. Is that how you define, right? Okay, great. So there is number of faults occurred within 6 miles. Okay? Then using this random variable, n sub 6, of course n sub 6 follows Poisson distribution. Okay? It follows Poisson. The desired probability is going to be n sub 6 is greater than equal to 2, right? Because the number of falls occurred within 6 miles is at least 2. So it's got to be greater than equal to 2. Is that right? So that's going to be 1 minus p and 6 is less than equal to 1. Okay, then this is going to be 0.2127, I believe. Or intuitively, you can use other distribution as well. What is that? Just like previous example, we can use Erlang distribution for this case. How do you define the random variable in this case? T sub 2. What is T sub 2? Right. So time of the second fault, right? So in that case, using the Erlang distribution, the same probability value can be obtained like this. So this probability means the second fault has found within 6 miles. Is that right? So that is identical to this probability up here. So I also want you to recall your memory. Last time we mentioned that the CDF, cumulative distribution function of the Erlang distribution, can be computed by Poisson distribution most of the time. Okay? Because using Poisson would be a lot easier, a lot more handy than using the Erlang distribution. Okay? Okay, I think that's all for today. So next time I'm gonna bring more in-class exercise problems. Okay, so we're gonna practice more about this. Okay, but basically it's gonna be very similar to what you've done today. Okay. Every time we meet with certain problem description, we will try to define random variable first. And then using that random variable we just defined, we're going to build up the desired probability. Okay? That's what you're going to do every time. Okay? Okay, thank you. I will see you all next time. Bye-bye.